Before starting this lecture, we need to distinguish between EMFs and currents that are caused by batteries and those that are induced by changing magnetic fields. If we use only EMFs or currents, we are talking about the EMFs or currents caused by a physical source, such as a battery. When we talk about EMFs and currents caused by changing magnetic field, we use a term with an adjective, induced. We have seen that when the magnetic flux through the area enclosed by the loop changes with time, an induced EMF is produced in the loop. This phenomenon is called electromagnetic induction. Today, I will show you some practical effects of this phenomenon. Please look at this figure. A circuit consists of a switch, a resistor, and a battery. When we close the switch, we observe that the current does not jump immediately from 0 to its maximum value. Why? Let me analyze the process in details. When the switch is closed, the magnetic field is established and the field lines penetrate the loop enclosed by the circuit itself, as shown in the figure. When the current is increasing, the flux is increasing accordingly, creating an induced EMF in the circuit. The induced EMF would produce an induced current in the loop, which would create a magnetic field opposing the change of the original magnetic field according to Lenz's law. Therefore, the direction of the induced EMF is opposite the direction of the EMF of the battery, which results in a gradual increase of the current to its maximum value. This effect is called self-inductance because the changing flux and the induced EMF are caused by the circuit itself. An EMF caused by this way is called a self-induced EMF. According to Faraday's law, the induced EMF epsilon is equal to the negative of the time rate of the change of the magnetic flux. We know that the magnetic flux is proportional to the magnetic field, and the field is proportional to the current in the circuit. Therefore, a self-induced EMF epsilon L can be expressed by this one. Epsilon L equals to the negative of the time rate of change of the current. Here, L is a proportionality constant. We call it inductance of the loop, which depends on the geometry of the loop. We know an induced EMF epsilon equals to minus d phi b over dt. If the circuit consists of a coil with n turns carrying the current I, we have this one, epsilon equals to minus n times d phi b over dt. From these two equations, we could obtain the expression for the inductance of an n-turn coil, L equals n times phi b over I. We could understand that the inductance is a measure of the opposition to a change in the current. The SI unit of inductance is a Henry. 1 Henry equals 1 volt per second per ampere. Well, let me give you an example to show how to evaluate the inductance in a simple situation. Consider a solenoid having n turns and length L. The turns are closely spaced and the length is much larger than its diameter. The cross-sectional area is A. Please find the inductance. We have known that the magnetic field B of an ideal solenoid equals to mu0 times little n times I. The flux passing through the area A of each turn is B times A, so we have this expression for phi B. Substitute this one into the equation above, the inductance of a solenoid is obtained. From this result, we can see that the inductance is dependent on the geometry of the circuit and also the permeability of magnetic materials. Now, if we have two circuits, when a current varies with time in one circuit, the magnetic flux through the area enclosed by nearby circuit changes with time. According to Faraday's law, an induced EMF was created in the nearby circuit. This process is called mutual induction. Let's look at an example as shown in the figure. Assume the circuit 1 carries a current I1, which has n turns of coils, creating a magnetic field B1. Some of the magnetic field lines of B1 pass through the circuit 2, which has n turns of coils. We use phi12 to represent the magnetic flux caused by the current I1 and passing through the circuit 2. Analogous to the self-inductance, the mutual inductance M12 of the circuit 2 with respect to the circuit 1 can be expressed by this equation. M12 equals to N2 times phi12 divided by I1. Mutual inductance depends on the geometry of both circuits and also on their orientation with respect to each other. For example, in this figure, if the separation distance between two circuits increases, the mutual inductance will decrease because the flux linking decreases between two circuits. In the discussion of this part, please note the subscripts of each quantity. If the current I1 varies with time, the EMF induced by the circuit 1 in the circuit 2, epsilon 2 equals to minus N2 times d phi 12 over dt equals to minus M12 times di1 over dt. In the same manner, assume the circuit 2 carries a current I2. The magnetic field B2 is created by the current I2. Some of the flux of B2 also passes through the circuit 1. We use phi21 to represent the flux caused by the current I2 and passing through the circuit 1. If the current I2 varies with time, the EMF induced by the circuit 2 in the circuit 1, epsilon 1 equals minus M21 times di2 over dt. M21 is called mutual inductance of the circuit 1 with respect to the circuit 2. In mutual induction, the EMF induced in one circuit is always proportional to the time rate of change of the current in the other circuit. The proportionality constants M12 and M21 are equal, so above equations are transformed into these two equations. Next, I'm going to explore the effect of an inductor in a circuit. What's an inductor? If a circuit contains a coil, as discussed above, the current in the circuit will not increase or decrease to its final value immediately due to the inductance of the coil. If the coil has a large inductance, we call it an inductor. An inductor is a circuit element and its symbol is shown here. But please note, a circuit still has some inductance that can affect the circuit's behavior even without an inductor. Please look at this figure here. A circuit contains a battery, a resistor, and an inductor which we call RL circuit. The internal resistance of battery could be neglected. When the switch is closed, the current in the circuit begins to increase, and an induced EMF opposing the increase of the current is produced in the inductor. It can be determined by this equation. For the circuit, we write down this equation, where IR is the voltage drop across the resistor. We could find a solution to this differential equation. From this result, we could see how the current increases with time in the RL circuit. Due to the inductance of an inductor, the circuit increases with an exponential function. Obviously, if L equals to 0, the exponential term becomes 0 and the current increases immediately to its final equilibrium. This is a plot of I versus time. Please look at this figure. We first throw the switch to 1. After the current reaches the maximum value, the switch is set from 1 to 2. How the current changes with time. This is an assignment for you. In the next lecture, we are going to talk about energy in the magnetic field.